an 8-bit value that's unsigned, which means no negative numbers. Like, it's just raw data. It's not an integer in the positive or negative sense. And let me just nickname that to byte, just to make clear that I want to manipulate files byte at a time. Let me now declare, for the first time today, a version of main that takes in an argc command, takes in argc and takes in argv, which is for command line arguments. Technically, though, I'm not using the CS50 library in this version, so even that can now be changed. And this is the canonical way in C to declare main when you want to get command line arguments using char star instead of string. So now I'm going to do two things. I want to open, remember how copy works. You specify two files, the file you want to copy and the new name that you want to give to the copy. So it would be like cp space old name space new name at the command line. So accordingly, I'm going to do this. I'm going to create one file in memory called source, or src for short, and I'm going to set that equal to whatever is in argv1 in read mode. But just to be super specific, I'm going to use read binary mode. I don't want to be copying text files. I want binary data, zeros and ones like images. So I'm going to tell fopen to expect binary data. I'm then going to go ahead and create a second variable called destination, dst for short. And I'm going to open up whatever's in argv2, the second file name at the command line. But I don't want to read this file. I want to write to it in binary using zeros and ones. Now, let me do the copying 1 byte at a time. It's a little inefficient. I should really do bunches of bytes at a time for speed. But let me just give myself 1 byte in a variable called b. So byte is not a thing in C. It's literally a synonym I created just for the sake of discussion, because we'll do this in the future as well. Now, let me go ahead and do this. How do you copy a file from old to new? Well, I think it would suffice to use a loop and just start at the beginning of the file, loop all the way to the end of the file, and within the loop, copy 1 byte from old to new. So how do I do that? I used fprintf last time to write text. This time, I'm going to use a different function as follows. While there are bytes to read from the file, and this one's going to be a mouthful, so let me just type it out and then I'll explain it. While that line is true, go ahead and write this line, which is similarly a mouthful, so I'll type it first and then explain what it does. Then I'm going to close destination. Whoops. Then I'm going to close source. And I claim, if I haven't messed anything up, this will now copy files for me. How? So this is indeed a mouthful, but there's a function called fread, whose purpose in life is to read 1 or more bytes for you. How does it work? Well, just like swap, just like scanf, you have to tell it where to load those bytes in memory. So if I want to put them in the byte called b, I can't just say b, because that's pass by value. I need to pass by reference. So I say the address of b is where I want you to put 1 byte from the file at a time. How big is a byte? Technically, I could just say 1, because we all know how big a byte is. But I'm just going to be super proper and generalize this as size of b, so it just figures it out for me, just in case we ever do more than 1 byte at a time. How many bytes do I want to copy at a time? 1, just to keep it simple. And where do I want to read those bytes from? The source file. fread, if you read the documentation, just tells you how many bytes were successfully read. Logically, it should either be 1 was read or 0 were read based on what I'm asking it to do. I'm asking it to read 1 at a time, so it's either going to succeed or fail. So I want to do this for as long as it succeeds, because it's going to succeed until it gets to the end of the file, and then there's no more bytes to read, at which point it will return 0. So now, I do the opposite with fwrite, and it's almost the same line. Where do I want to write that byte? Well, first, I tell fwrite where to find the byte. Go there and get the byte that was copied. It's this size, which is going to be 1, but I did it generally. 1 byte at a time, please, and write it to the destination file. So if I now open up my terminal window, let me first make cp to create my own copy program. Let me actually open an image I came with today. Here's a happy cat from the internet, and that's going to be my original image. Let me now go ahead and run this, /cp. I have to run / because I want my version of cp, not the one that comes with Linux. So /cp cat.jpg, and let's call it maybe my backup cat, just in case I ever mess up the original. Enter. Seems to work OK. When I run now code of backup.jpg to open the copy, there is that same happy cat. So it's very low-level manipulation, but it all results from my now having the power to express myself in terms of locations in memory using pointers, understanding that strings and now files are really just abstractions on top of these lower-level details. And from all of that is going to come some pretty powerful functionality. In fact, among the things that you can now do, as you'll soon see, is manipulate at least simple files known as bitmap files. So BMP is bitmap file, and it essentially implements images exactly as we began today, as just a map of bits, a grid, XY coordinates of grids, each of which represents a pixel coordinate. A bitmap is a type of file with a .bmp file extension on a computer that stores images just like that. And now that you have the ability to not only think about images in this way, but write code that manipulates images, you can do powerful things a la Instagram and TikTok and Snapchat like filters nowadays. So for instance, here is an image of the bridge, the Weeks Bridge across the river. Here is a black and white filter that we've applied by writing some C code, as you soon will, to change it from colorful to black and white. Here's the original that you might see every day. Here, meanwhile, is a reflection thereof. If you've ever flipped an image around on the x-axis, this can actually rotate the image, even though this is the other side of the bridge over there. Meanwhile, here's a blurred version. If it looks a little blurry, like that's deliberate because we've essentially smudged all of the values by looking at every pixel, looking up, down, left, and right, and kind of blurring the effect to give it this effect here. Here is what's called edge detection, whereby if you're feeling more comfortable, you can write code that looks at these individual pixels, tries to figure out where the edges are, just like a fancy computer might, and then colorize it in this way as well. And you'll be able to do all of that because images like these are just grids with coordinates with lots and lots of pixels. So what started quite simply now is going to be something you now have complete control over now that we've taken off these training wheels. And it's cultural within computer science to understand geek humor like this. And so the last thing we'll do today is give you this joke to end on, which for better or for worse should now make sense. And those chuckles will suffice. This was CS50. bytes to read. But first, make CP ahead and run this from the internet. And that's going to, I have to run essentially stacked tails ending that express go ahead, not the one that seems to work okay. When I run now code of backup.jpg to open the copy, there is that same happy.
Okay, well, hello one and all, and welcome to CS50's fourth section this week. My name is Carter Zenke, and I am the course's preceptor here on campus. And this week, week 4, we learned about memory and how our computer actually stores things in bits and bytes across its own landscape of bits and bytes. And so our goal today will be to talk about a few different topics, most of them from lecture, and to give you the chance to ask the questions you want to ask so you can prepare yourself for this week's problem set. So among these topics are this idea of pointers and why we would even use them. So as we saw in lecture, a pointer is a way of storing some address in a computer's memory, kind of similar to a variable. We'll also talk about how we can read and write data to files. So up until now, you've been writing programs that maybe take user input and print something back to the screen. By the end of this section and by the end of this week, you'll be able to write programs that actually open up files and can actually write data to files, getting more advanced along the way. And all this will hopefully prepare you for problem set 4 at the very end. So I'm excited to dive into these topics today. Now, the first topic will be this idea of pointers. And they are admittedly a little bit scary. I've seen a lot of fear around pointers when we talk about them. And I think they're scary because they introduce some new syntax that doesn't feel quite familiar yet. And so the goal is to help you become familiar with that syntax so you can actually leave feeling a little bit less scared of pointers and more empowered to use them at the end of the day. So I think one thing that makes pointers less scary is this idea that they really tie closely to an idea you already know about. And that is this idea of a variable. So if you remember back in, let's say, week 1 or so, we talked about this idea of a variable. And in this section, we had this idea of trying to make a contact application to store, let's say, the number of times we had called somebody on the phone. And so we had this variable named calls, and this was our visual of that variable. We had a box that had some value in it, like the number 3, and that box had a name called calls. And we said that a variable was exactly this. It is a name for some value that can change. That is, the value of that variable could change. It could be 3 calls right now, but when I call somebody anew, it could be then later on 4 calls. So some value that can change. But what we didn't see in week 1, which we'll now see this week, is that this value has to be stored somewhere in our computer. It can't just be out in the ether. It has to have some actual physical location among all the bits and bytes inside of our computer. And that is what we called an address. This value has some address inside of our computer. And so in lecture, we saw this kind of grid of addresses, of bits and bytes, kind of like a yellow grid. We could store number 50, a pointer, and so on. I want to give you one other visual way to think about pointers and addresses too. So you could think about it as well as kind of like this table here, where your computer has keeping track of both the addresses of values and the values themselves. That is, what is the value I'm storing, and where among all the possible bits and bytes am I storing that value? And so notice here that we have addresses that begin with 0x. 0x. And I'm curious, as a question for you all, what do you remember 0x meaning or signifying? Why do we always append, or really prepend, this 0x? So I'm seeing some right answers here, which is that this means hexadecimal. So whatever comes after 0x is a hexadecimal value, which is to say it's a base 16 value. So you're probably used to the base 10 system, like decimal. You've seen in this class the base 2 system, like binary. And now we're introducing a new one called base 16, which is just handy because we can count up to larger numbers without using so many digits. Like if we're talking about the many billions of bits that are inside of a computer, it's worth representing them in a way we can count pretty high with some fewer number of actual digits we'll see as part of our number we're writing out. So that's the background for this address here. But to keep going with this idea, our computer wants to store some value somewhere in memory. And so for that calls variable we saw earlier, well, that could be stored at this address right here. 0x, let's see, 50, 5, 0, 0, 0, 5, and 7 zeros. So 0x, 5, and 7 zeros. Somewhere, doesn't quite matter. It has some address in our computer. And the way we put it there was this C syntax on the right. We simply said, we're going to create some new integer whose name is calls that will get the value 3. We're going to store it somewhere in memory. Now, a pointer is this exact same idea, but the only difference is that we're not going to store an integer or a character or really a string or anything else. We're going to store instead an address itself. So here's what we would say if we're going to make a pointer. If we go here, notice how on the next table row, I'm not storing an integer or a character. I'm storing an address itself at some address inside the computer. And notice in particular that this address I'm storing, 0x, 5, and then like 7 zeros afterwards, that seems to reference some other address in my computer's memory. That is the place where the 3 is stored. So we could say that this value, 0x, 5, and 7 zeros, that is pointing to this other address where the 3 is stored, and therefore it is a pointer. So the only difference here is that we're no longer storing integers or characters or so on. We're now just storing addresses at some place inside our computer. So let me ask, what questions do we have on this so far? On this mental model, or on this idea of now storing addresses and not just actual values like numbers or characters? Okay, not seeing any so far. Actually, I'm seeing a question here. How can we dereference this pointer? It's a good vocabulary word we learned in lecture, which is to go follow a pointer to the place it is pointing to. So let's begin with a bit of syntax here. And here, if I show you this in full screen, you'll see that this is the syntax we could use to do exactly what we did on the table on the left. Let's create now a pointer whose name is p, and we're going to store the address of this variable named calls. So notice a few pieces of syntax here. We have int star, which means this is no longer an integer, but it is a pointer to an integer. It is going to direct us. If we dereference this pointer, we're going to end up at an integer in our computer's memory. And notice too this ampersand, which means we should store the address of whatever calls is storing, in which case we see in the table here that is 0x5 and then 7 zeros afterwards. So the data type of p here is a pointer, but it is a pointer to an integer and not a character, for instance. So to highlight here as well, let's try setting this up and visualizing it a little bit more. So all we're doing is saying the same thing we did for a variable, that p, this value named p, should store this particular address now. And I think it's worth breaking down the syntax on the left so we actually see it and you can use it later on in your own programs. So one common point of confusion here is that this variable, this pointer, is not called star p. That is not its name. In fact, it is just called p. But it is confusing, though, because we see int star p. Like the star is right next to the p, and so we kind of assume, well, this pointer is just going to be called star p later on. But in fact, it's just a syntactic trick. All we're doing here is saying this is a pointer named p, and its type is int space star, or a pointer to an integer. So when you see this star being used to initialize or declare some value, kind of be careful here and think, what is the name of the variable that I'm working with, or the pointer that I have, and what is its type? Because it might not be quite apparent to you if you're new, that you might say, okay, well, the star is next to the p, maybe that's its name. It's not. P is its name, int star is its type. Now, it's more obvious than on the right-hand side here that the value is simply the address of calls using the ampersand here. And as we saw in lecture, I like to think of this as ampersand for address. Both begin with A in this case. And a question here is, could we actually modify this syntax and say maybe int no space star space p? That's absolutely possible, as we saw in lecture. We could also have int space star space p, which would be maybe a little more confusing in my opinion, but that would work as well. So white space doesn't quite matter, but by convention, we tend to use this syntax you're going to see here, int space star followed by the variable name. Now a question here too is, what if we wanted to store not just an integer, or a pointer to an integer, but a pointer to a character, which as we saw is kind of like what a string would be? Well, in that case, we'd simply replace the int part of this syntax with a char, or char, C-H-A-R. That would then store a pointer to a character. And the follow-on question is, well, if we can store a pointer to an integer, a pointer to a character, could we have a pointer to a pointer? You could. There's nothing stopping you. You could have a pointer to a pointer to a pointer, and so on and so forth. But at that point, I'd say we're getting a little bit ridiculous. We can kind of pause and say, what are we actually doing here? But you could possibly do it. So to recap here, some key syntax to study, to practice with, is going to be the following. You could say that type space star is getting in your head is a pointer that stores the address of a certain type. But then later on, as we'll see, if I want to dereference that value, that is, get the value that that pointer is pointing to, I would use the star in a different way. I would say star, and then the name of that pointer. So star x, for example, takes a pointer named x and gets the value that is stored at that address. As we just discussed here, ampersand x takes x and gets its address. Ampersand for address, or A for A in this case. So questions on this syntax here. Question about how pointers work with arrays. So we'll see this probably a little bit more as you work on the problem set and go on with the course. But you could think of a pointer as pointing to the beginning of some chunk of memory. In the previous example, we saw a pointer pointing to one particular value, like one integer or one character. But there's something stopping us from having a pointer that points to an array of values or a list of values, all back to back to back in a computer's memory. So we can have pointers to arrays. Other questions too? Okay. So I think one question that comes to my mind when I first see this idea of pointers is, that's all fine and good. I love pointers, I love addresses, but why would I ever use them? Because at this point it seems kind of confusing. Like, why would I use this syntax versus the one I already know? And why is it worth getting into the weeds about all these addresses when I can just store things wherever, right? I don't quite care. Well, there are a few reasons you might want to use pointers, and pointers can enable you to do things that you actually couldn't do before. So among them are these things that you can now do with pointers. You could now write a function that allows you to pass something in by reference and not just by copy. So that is to say, I could have a function that modifies some value right where it currently is. And this is helpful more so as you'll see next week. When we make these very big data structures, I could write functions that modify those data structures without copying all of them somewhere else. And perhaps more resonate probably this week is this one, which is you can use what we call dynamic memory. That is, up until now, you've been writing programs that use some fixed amount of memory. The user might type something in, maybe it uses some maybe 5 bytes or 10 bytes or so on, but you could now, as the program runs, actually ask your program for more and more memory depending on what the user actually needs. And you can use pointers to manage memory for you. So more again on that in some future weeks, but pointers here are setting up these additional capabilities that you can use as we go through the course as well. So I hope you find at least some of this exciting. And I want to focus in particular on what we can actually do because of this. So in this first step, it's like, OK, great, I can write functions that pass things by reference and not by copy. But what does that get me ultimately? Well, ultimately, if you write functions that allow you to pass values by reference, not just by copy, you can write code that's ultimately cleaner as a result. And as I said before, you can also now scale your usage of memory in your application by using pointers to actually manage that memory and make your programs all the more efficient too. All right, so let's keep going here and show a bit of a visual example of what it means now to pass things by reference and not just by copy. So we saw in lecture, we had this idea of trying to swap two values around and trying to write a function to do that. So let's revisit that and kind of get a visual example here in our slides so we understand exactly what it means now pass things by copy as opposed to passing things by reference. So you could imagine here we have some code on the left-hand side and what we call our call stack on the right-hand side here. So you could imagine we have already called main, the main function of our program, and we've set two variables, one equal to 10, called A, and one equal to 50, called B. And in our first implementation of swap, we had the following code, that swap would take an integer named A and an integer named B, and it would swap them around, trying to store the value of B in the place of A and the value of A in the place of B. So visually, it look a bit like this, where I have main running, but now as soon as I call or use swap, I'm able to have another function call. I'm kind of copying down those values from main. So to show the animation one more time, we had main running, but now we call swap. We pass in these values A and B. We pass them by copy. This space that swap has gets a copy of the values for A and B. And then, of course, within swap, we do swap them. So the value of A gets 50, or the variable A gets 50, and the variable B now gets 10. But what's the problem? Like if I finish now running swap, what do you notice? They seem to be swapped in swap, but what hasn't happened actually? Yeah, so in main, they're still the same. I see that A is still equal to 10, and B is still equal to 50. So if we call a function without using pointers, we're essentially saying, let's go ahead and take a copy of these values, put them somewhere else, and do something to them. We won't actually impact the variables we were hoping to impact when we set them or use them in main. So once swap finishes, we're still left here with the same values in the same places. So what do we do to fix this in lecture? What do we do to fix this problem? Any ideas? So we did end up using pointers, and what we did in particular is we didn't copy in the actual values of A and B. We copied their locations or their addresses, that is the pointer to A and the pointer to B. So another option here is to rewrite swap so that it does this instead. So notice in the syntax now, this swap function is taking two arguments, one that is now a pointer to A, and one that is now a pointer to B. That is the address of A and the address of B. And then down below, it's going to use the dereference syntax to go and get those values and swap them in place. So although we're still running swap and we're copying in some value, the ultimate result, though, is that we actually copy in the address and we change the values exactly where those values currently are in memory. So for instance, let's visualize this. I'll show you. We're going to call swap here. Here's swap. And what we pass into swap now is not the value 10 or the value 50, but the address of A and the address of B. So now we have a link from swap's location memory back to main, where A and B originally are. Now, if we follow the steps in swap, we can follow these pointers and swap the values all at once in place. So now A is 50 and B is 10. And so as you go on in the course, you'll be able to write functions that do this, not just for two variables, perhaps for entire data structures, and that allow you to ultimately build up much more complex ways of storing data in your programs. So questions then on this idea of swapping and passing by reference and passing by copy? A question here, if you wanted to access the address, wouldn't you write &A and &B? And in fact, you would. In this case, though, as we see in void swap int star A, int star B, what we're defining here is the definition of swap. And you'll see swap takes two arguments. The first argument is a pointer to A. But how do we know it's a pointer to A? Well, we see here it has the type int star. And then the same thing here, a pointer to B. We know it's a pointer to B because the type is int star and the name is B. So I think it's helpful actually to show you the entire code for this as well. And for that, I'll pull up my code space and I'll actually walk through each step of this now with debug 50 so we can see the exact values of each variable here and understand exactly what's going on in our program. So I'll come to my code space and now I will code swap.c. So swap.c is already done for me. I already wrote this code. But let me show you a few pieces here. So on line 4, I have the prototype for my function swap. Swap will take a pointer called A and a pointer called B. It won't return us anything. It will simply have the side effect of swapping those two values. Now, in our function called main, the very first function to run in our program, I'll create this variable named A, put it someplace in memory, and give it the value 10. Similarly, I'll create this variable named B, put it someplace in memory, and give it now the value of 50. So first, I'll print out what is A and what is B. I'll call the function swap, and notice now I'm going to give it not the value of A, but the address of A. That is, wherever A is stored, I'll pass that into swap, and in the same way, I'll do that for B. And then, once that's done, I'll call printf, and I'll tell us again what is A and what is B. Now down below, here's swap, the same implementation we had before. We're going to take in a pointer called A and a pointer called B, and through what we saw in lecture, we're going to swap them all at once down here. So let's go ahead and write a bit of syntax here to actually debug this program and see it step by step. So if you're familiar with debug 50, we can actually pause our program and walk through it step by step, seeing the values of variables as we go. So I might pause this program here, right where we're about to call swap. And now, if I make swap to compile it and run debug50./swap and hit enter, I should be whisked away to the debug 50 environment. And I should hopefully see here soon that I'm able to see my program running, but paused at this point. So now I want to show you where we are. Notice in my terminal, I see that A is 10 and B is 50. And actually, in this tab over here called variables, I can see that in real time. I do see A is 10 and B is 50. So it's true, right? Now, down in my call stack, notice that main is currently running. It's the highest thing in my call stack. So now I want to run swap. But if I want to see the workings of swap, how swap is actually going to swap these two values, I should use step into, which means run this function, but show me each step along the way. So I'll step into swap here, and notice how I change my variables. These are the variables that have been passed into swap. I see this variable named temp that currently has value 257. Why do you think it has that value? Any ideas? Doesn't seem to make much sense to me. And we learned a name for this value in lecture, or rather this type of value. I'm seeing some people say a junk value or a garbage value. That's exactly what it is. It's some garbage value. It is a value that is just kind of already there in memory. We haven't assigned it anything yet. But once I actually step over this line of code, we should see what? Well, int temp, this value here, is currently 257. But once I run this, I'll set it equal to the result of dereferencing the pointer A. Notice the value of A here is 0x7ffd26c1790c. Okay? But what is at the end of that pointer? If I follow it, what will I find? I'll find 10 here. So notice that it gives us the value not just for a, but the value of star a, that is following the pointer, going to that location memory, and finding whatever value is there. In that case, that value is 10. So it goes to say that if I were to run this line of code, line 18, I should set temp equal to 10. That is the value that I would get if I dereferenced a. So now I'll step over it, and I'll see temp becomes 10. Now what's the next step? Well, this says star A equals star B, which is kind of confusing, but keep in mind what star A is. Well, star A is currently 10. It is the value at the location that A is stored. Now I want to put in the value the value that I get if I follow the pointer B, which is 50. So notice here, star B is 50. If I follow this 0x7ff d26c17908, wherever that is in memory, if I follow that pointer and find that location, I will then get the value 50. And I'll then assign that value to the dereferenced part of this pointer A, which is currently 10. So I'll step over this now, and we'll see, well, star A becomes 50. I follow that pointer to the location of A and set it equal to 50. Now then, I'll say star B gets the value of temp. Well, star B is currently 50. I'm going to follow this pointer B to its location, to its value, which is 50, and then I'll set it equal to 10. I'll step over, and now I'll see star A is 50 and star B is 10. Now if I end this program, finish swap, what do we see? Well, A is now 50 and B is now 10. I'll step over and finish my program again, and now I'll see A is 50, B is 10. I've swapped these two values right there in place, walking through step by step. So I'll close this program, and let me ask, what questions do we have on swapping or on pointers so far? Question here, why is swap defined on line